All right, I forget which ones. Did we do A and B yesterday? Yeah. We finished those? Okay. Let's check out C. All right, inside that polar graph, but outside the other. All right. Let's draw a picture. So on our calculator, you could utilize that. Maybe you know what some of these are going to look like. 3 sine is a circle of length 3 on the y-axis. And then length. So that 3 is actually the diameter. It looks like the other one's a kind of a cardioid shape. No!
My school was built in 1907. 1800s. This school?
on one page. It's 7.4. Yeah. I know. I mean either. That's true, but you're gonna do it to you know what I mean?
Some people say $20 is $20.
It's required.
All right, can we get that graph? Let's see, if we want inside the circle but outside the cardioid, looks like we're looking for that area. What might be useful to know? The intersections. All right, so 3 sine equals 1 plus sine. We can subtract a sine, divide a 2. When does sine equal a half? Five or six, good. All right, so there's the first intersection. Instead of going up pi over 6 from the right axis, if we were to go up pi over 6 from the left axis, aka taking pi and then subtracting pi over 6 because we're going backwards, that would leave us with another one of 5 pi over 6. All right, so if you were to imagine starting with an angle of rotation of pi over 6, and as you travel or rotate to the 5 pi over 6, notice how you always have the same outer function and the same inner function. It never changes, right, as you rotate? Okay, perfect. So we don't have to worry kind of about like switching bounds or things because we're always looking at the same functions as we rotate. So let's go ahead and check out the area. We'll have 1/2. Our bounds are pi over 6 to 5 pi over 6. And then we need the outer radius squared minus the inner radius squared because we have those two functions to consider. So the outer radius is that 3 sine function, and the inner radius is that 1 plus sine. All right, calculator from there. I got 3.142. Does that check out with what you got? Good. All right. Let's try another one. We'll check out D. The common interior of those two. So 3 cosine would be a circle of length 3 on the x-axis. And 1 plus cosine, we just did 1 plus sine and that was a cardioid shape. So 1 plus cosine would probably be another cardioid shape just on the x-axis. So maybe something like that. You could use your calculator though to help you out. All right, so we want the common interior. That's probably this section here. All right, let's find some intersection points. 3 cosine equals 1 plus cosine. When does cosine equal a half? Pi over 3, good. So that's in the first quadrant, that's this one. And then the other one would be in the fourth quadrant, that would be 5 pi over 3. All right. Let's think about this. So we normally start with an angle of 0. That's where we're starting on that horizontal axis. And if we were to go through kind of our rotation, notice how if we were to start this way, we would be touching the cardioid shape. And as we travel through, we're still looking at the cardioid. But the moment we get to the intersection point, it starts to change. Because then I start to touch the circle after that. Do we see that? So since we're looking at a different function, we're going to have to probably change our bounds as we go through the area calculation. And maybe we can use symmetry to our advantage because we have the same area above as we do below. So we can maybe multiply by 2 eventually. Let's just check out starting at 0 and rotating through to see what that area might look like. So if we start at 0, we said we were always looking at the cardioid shape until we got to that pi over 3. So we'll use the cardioid function for that area. But after pi over 3, we started to look at the circular function, which was the 3 cosine theta. Where do you think the bound is going to end? If we're at pi over 3, looking at it this way, as we keep rotating, what angle do you think would bring us back to the pole? Pi over 2. Good. Because remember, we're only looking in the first quadrant, and that goes from 0 to pi over 2. So we kind of have to stop at that pi over 2. So this formula we have here is only for the area above the x-axis. Let's keep that in mind. So we'll let our calculator do the work from there. Let's see, I got 1.963. All right, so then we'd have to double that to get the additional area underneath the x-axis. So times 2, we'd get 3.927. We're doing okay? We're starting to get a little bit more comfortable with them the more we do? I hope. All right, let's try the last one. Common interior, 4 sine of 2 theta and a circle of radius 2. All right, so 4 sine of 2 theta, that's going to be kind of a flower type shape because we're going to have to double the amount of petals we have, and they should have a length of 4. So maybe we can just graph them so we know where they're showing up on the coordinates, on the coordinate grid. So 4 sine 2 theta and 2. All right, so there's our graph. And if we want the common interior, we have all of these areas to calculate. Do you feel like calculating all 4 of them? No. What do we feel like doing then? There you go. Let's calculate 1 and then we'll multiply it by 4. Okay, we'll use that symmetry idea. All right, so let's maybe find some intersection points because we have a lot of them. We have 1, 2, 3, 4, 5, 6, 7, 8, but we only really need to calculate 2. Maybe we'll work in the first quadrant. Okay, we'll figure out this area and then just multiply it by 4. All right, so intersection points. When does sine have a value of a half? Pi over 6. And 5 pi over 6. So we'll divide both of those by 2. We'll get pi over 12 and 5 pi over 12. All right, so the first intersection point is pi over 12. And the next one is 5 pi over 12. All right. So it might be a little hard to visualize just because of how small we drew this, but I'm going to go ahead and draw it a little bit bigger just so we can see this. If we're looking at the first quadrant and we have the semicircle or the circular part, and then we have the petal, something like that. And remember, those are our intersection points. If we start with an angle of 0, okay, we're looking this way, and then as we rotate, notice how we are initially looking at the petal portion, and then the moment we get to the first intersection point, we are then looking at the circle. But then the moment we get to the next intersection point, we start to look back at the petal part. Do you see how it changes as you go through? Okay, so we might have to have multiple integrals. We're going to have to use the first integral where we're looking at the petal, then the next integral is looking at the circle, and then the last integral would be looking back at that petal again. Okay, and we're only looking in the first quadrant, so let's keep that in mind. Let's see if we can write these different integrals. Okay. So our first one, we would start at a rotation of 0. And if we start at the rotation of 0, we said we were looking at the petal initially. So that was the 4 sine of 2 theta function. And when did we stop looking at the petal as we rotated through? Pi over what? It was that first intersection point. Pi over 12. Good. All right, but we still had more rotation to go through to calculate all this area, so we're going to have to add another integral. After that pi over 12 rotation, we started to look at the circle, which was just 2, and we stopped looking at the circle when we got to the next intersection point, which was 5 pi over 12. but we still had more area to calculate. So another integral, we'll have to go from 5 pi over 12. And then we eventually got back to the pole, so we were done working in the first quadrant. The first quadrant ends at a pi over 2 value. And we were looking at the pedal in that last portion, so we'll have to use the 4 sine of 2 theta function. Okay, so it's a bunch of calculus and integrals, but it's calculator work for you to type it in. So go ahead and take the time to type in those 3 integrals. Let's see, I got 2.457. Is that okay? All right, so that's just the area in the first quadrant for that first pedal. They wanted all of the common interior, so we have to multiply by 4, and that would give us 9.827. Sound good? All right. Let's see. Tomorrow, a lot of us aren't going to be here, so we'll just use it as kind of a practice day for these, or quiet study hall if you want to do that. But we're going to have partner quiz Monday, or class quiz Monday, review Tuesday, and then our very last unit test Wednesday into Thursday if needed. All right?